In this video, we're going to discuss another way that we can calculate the enthalpy change of a chemical reaction based on pre-existing data. So we'll be using a type of data known as the standard heat of formation, which is defined as the enthalpy change for forming 1 mole of a compound from its elements in their standard states. So a few things to consider here. First, this idea of standard state of an element is just how it exists at normal laboratory conditions at typical room temperature, which is considered to be 25 degrees Celsius and typical atmospheric pressure of 1 atmosphere. So we refer to these conditions as standard laboratory conditions. And again, that's room temperature and 1 atmosphere of pressure. So standard states of the elements, you don't need to memorize them all or anything. Most everything is a monatomic solid. So if you're ever not sure, it's probably the way to guess. Things that are diatomic, you should be aware of. So there are 7 diatomic elements. They are hydrogen, nitrogen, oxygen, and then the halogens. So these always exist as 2 atoms connected together. Most of these are gases, but bromine is a liquid, iodine is a solid, is their state of matter at room temperature. There are only a handful of gases on the periodic table. The noble gases, of course, that entire family. The last column on the right on the periodic table, also known as group 8A. So those are all gases, as well as nitrogen, oxygen, the diatomics I just listed as gases, fluorine, and hydrogen. That's all. For liquids, we only have 2. Bromine, I already mentioned, is a diatomic liquid, and mercury is the other one. Everything else is solid. Under standard lab conditions. And anything else I give you, you can assume is monatomic, is just 1 atom. That's not quite true of everything, but for the examples that I'll use, it will be. So be aware of those, that's what it means for something to be in standard state. For these things, they exist as diatomic in whatever state of matter they are. Everything else we'll consider to be monatomic, gas, liquid, or mostly solids. So these heats of formation that we're talking about today are the delta H for what's known as a formation reaction. Which is always elements in their standard state forming 1 mole specifically of some compound is how a formation reaction is defined, and therefore how heat of formation is defined. So for example, if we wanted to write the formation reaction for carbon dioxide gas, carbon dioxide gas is going to be my product. The elements that carbon dioxide is comprised of are carbon, which is a solid, and oxygen, which is a diatomic gas. So carbon plus O2 forms CO2 would be the formation reaction for carbon dioxide, and the delta H of that reaction would be the heat of formation for carbon dioxide gas. So let's try another example. Let's look at H2O. Why don't you pause here and try to write the formation reaction for liquid water. So in writing this formation reaction, the compound that we are interested in is always going to be the product. Our reactants are going to be their elements in their standard state. So hydrogen and oxygen are the elements that we're using here. And if we look back up here, both hydrogen and oxygen are on our list of diatomic elements. That means as an element, hydrogen exists as H2, oxygen exists as O2. So that is how we have to use them in this context. They are both diatomic gases. So even though we only need one atom of oxygen, we have to use a molecule of O2. But to balance this, we're going to put a coefficient of 1/2 in front of O2. By definition, a formation reaction only forms 1 mole of the compound as its product. That is part of what makes a formation reaction a formation reaction. So this coefficient has to stay 1, which means that H2 is fine as is. O2, I only need 1 atom, so I only need 1/2 mole of oxygen to react with every mole of hydrogen in order to produce water. So we can use formation reactions with Hess's law, just like we did in the last video, just using these as our steps to find the delta H for our overall reaction. So literally doing exactly the same thing. Why don't you pause here and give that a try? So in solving this problem, we need to do the same kind of stuff we were doing last time, that we're going to put everything on the right side in the right quantity. So I want to think about what's on the left, what's on the right, what do I need to change? So in my overall reaction, I'm looking to have 2 moles of NO on the left side of my reaction. Currently, the only place I see NO is in reaction 1 on the product side. So reaction 1 is the formation reaction for nitrogen monoxide. So we can see that 1/2 mole of N2 are reacting with 1/2 mole of O2 to form 1 mole of NO. So this is a formation reaction. And the delta H of that is the heat of formation for nitrogen monoxide. So in order to make this useful to us, we're going to need to reverse this reaction to get NO on the left side where we need it. And we're going to need to double it because we need not 1 mole, but 2. And we've only got 1 over here. So when we do that, we reverse our reaction and double it is going to put 2 NO on the left, and then N2 and O2 on the right. So we don't need this version of the reaction anymore. We reverse and double. So we are going to change the sign of delta H and double it as well. So that is going to get us a revised delta H here of negative 180.5 kilojoules per mole. So it was positive. We changed the sign to negative because we reversed the reaction and we doubled all the coefficients, so we doubled the value as well. So we don't need this one. Eventually, we will use the revised version in finding our final answer. So for the next thing, we've put the NO where we need it. So we have 2 NO on the left side here, which is what we were looking to achieve. The next thing in my reaction, if we're just kind of going in order, trying to make the pieces fit, is oxygen. But this one's a little bit more complicated because I have oxygen in reaction 2 and I have oxygen in reaction 1. So there are going to be multiple different ways that I can end up with one oxygen on the left since it appears in multiple places. So we're actually going to leave this one alone for right now, and it should fall into place in the end. Whenever that's the case, that you have something that appears in multiple reactions, leave that for last. It should sort itself out. If we move on to our next item in our reaction here, we need to end up with 2 NO2 on the right. Currently, we have 1 on the right, so it's in the right place, but we don't have the right number. So all we need to do here is double this. So we don't need this one anymore. We will double our delta H as well, which gets us 66.36 kilojoules per mole for this one. So now we were looking to put 2 NO2 on the right. We have achieved having 2 NO2 on the right. So this new delta H is the one that we're going to want to use. So now that we've taken care of everything else, we should circle back and make sure that oxygen actually worked itself out, and then that everything else cancels. So we're looking to have 1 oxygen on the left. Currently, we have 2 oxygen on the left and 1 on the right. It appears on both sides, but not in equal quantities, so some of it is going to cancel out. So the 1 oxygen that is on the right side in reaction 1 is going to cancel out 1 of the 2 oxygens in reaction 2 on the left, leaving us with 1 left over, which is exactly what we want. Then we should make sure that everything else cancels out. We have nitrogen on the left, nitrogen on the right, so those will cancel out as well. So now we have 2 NO on the left, which is what we want. We have 1 O2 on the left, which is what we want. 2 NO2 on the right, which is what we want. So now reaction 1 plus reaction 2 correctly adds up to our overall reaction, which means that we can take our revised delta H values based on the transformations that we did and add those together in order to get our overall delta H value, which comes out to be negative 114.14 kilojoules per mole. So we can go through the whole Hess's law process just using formation reactions, but when all of your steps are formation reactions, like the example we just did, we can actually simplify the process into a single equation that we can use. So when all of our steps our formation reactions, we can simplify the process. Since formation reactions all have so much in common, that there's only 1 mole of product and it's always coming from elements on the reactant side, we always end up doing pretty much the same things. That for anything that appears on the reactant side, we have to reverse our formation reaction. For anything that's on the product side, we don't have to do that. It stays the same. Whatever my coefficient is for that thing, I end up multiplying by that coefficient. So because there's only, let's use this one as an example, because there's only 1 mole of NO2 produced, I have a coefficient of 2, I have to multiply by that coefficient for that formation reaction. So we can kind of standardize this into a single formula because we're using all reactions that are so similar, because all of our formation reactions have so much in common. So the equation for this looks a little intimidating, but it's not so bad once you break it down. So this symbol, if you are not familiar with it, just means take the sum. So we have take the sum. The I, this is a lowercase I here, is just representing the coefficients from your balanced reaction. And then our delta HF is our heat of formation, which is data that you would be given. So all this is actually saying, all together, is that you're taking the sum of the heats of formations of your products multiplied by their coefficients. And you are subtracting the same thing for the reactants. So you're taking the sum of the heats of formation of the reactants, also multiplied by their coefficients. So you're just taking these pieces of information and subtracting. It's a lot easier when you see it in action. So from the previous example that we did out the long way with Hess's law, we were given the formation reaction for NO with a heat of formation of 90.25 kilojoules per mole. And we were given the formation reaction for NO2 along with the heat of formation of 33.18 kilojoules per mole. So that's all we were given. You will notice that we were not given anything for oxygen, but we don't really need anything for oxygen because elements in their standard state, the heat of formation is always 0. And if you think about the definition of heat of formation, that should make some sense. The heat of formation is the heat transfer to form something from elements in their standard states So forming an element in its standard state from an element in its standard state isn't changing anything. So if nothing is changing, no heat is being transferred. So anytime you have a pure element, the heat of formation is 0. So you don't need to be given that information. So if we want to calculate delta H for this process, we did it above the Hess's law way from the last video, but we can also just apply this formula since we are working with heat of formation and formation reactions for all of our steps in that Hess's law process. So finding our delta H, we want to start on the product side. Our products were NO2, so we're going to find the heat of formation of NO2, which was 33.18. And we're going to multiply that heat of formation by the coefficient for that substance. So the coefficient for NO2 is 2, so we'll do 2 times 33.18. And then that takes care of our products. We only had one product, so we don't have to add anything together. From that, we're going to subtract the same type of thing for the reactants. So on the reactant side, we have NO along with its heat of formation, and we'll take that heat of formation and multiply by the coefficient. So we'll do 2 times 90.25. And then we also have oxygen over here, which has a heat of formation of 0. You don't have to include that in the calculations. Clearly, it doesn't make a mathematical difference. I usually do just for kind of mental bookkeeping purposes, that when I'm checking my work, I like to see I have 1 product and 2 reactants. I have 1 product and 2 reactants. So it helps me keep track of my work personally, but obviously it doesn't make a difference to the math, so you don't have to include it if you don't want to. But when we do out this calculation, we get negative 114.14, exactly the same result that we found by Hess's law. We're literally doing exactly the same math, just in a more formulaic way as opposed to the more visual flip stuff around and multiply version. So let's look at one more example. So why don't you take a minute and try to solve this one. So I put the equation up at the top here. Again, you're going to take the heat of formation for each of your products, multiply by its coefficient, add all of those things together. Do the same thing on the reactant side, and then products minus reactants to get your final answer. So for this one, our products are where we want to start. We've got carbon dioxide and water on the product side. So in calculating our delta H, on the product side, we have 4 carbon dioxide. So we have 4 CO2. Our heat of formation for CO2 is negative 393.5 kilojoules per mole. And that's representing 1 mole of our stuff, which is why we multiply by 4, why we multiply by our coefficient. And then also on our product side, we have water. So we're going to want to add to that. We have a coefficient of 2 in front of water. So we'll multiply our heat of formation by 2. And then that is going to take care of the product side of things. So we have 4 times the carbon dioxide value plus 2 times the water value for heats of formation. And remember that this symbol just means add them together, so the sum of everything on the product side. And then from that, we're going to subtract the same process for the reactant side. So on the reactant side, we have 2 moles of acetylene. So we'll do 2 times the heat of formation for acetylene. And then oxygen, we're not given a value for, but we recognize that O2 gas is an element in its standard state. So the heat of formation is 0. Again, not mathematically important to include it, but for mental bookkeeping purposes, I like to keep things organized and account for everything in my calculations. So when we do out this math, we should find negative 2511 kilojoules per mole as our final answer.